Good morning, and welcome to today's webinar titled CO2 Delivery Techniques for Plastics, Foams, and Pharmaceuticals. Hello, my name is Dale Clay, the Syringe Pump Associate Product Manager, and I will be your presenter today. We'd like to invite you to use the chat feature to send messages at any time during the presentation. We'll answer the questions at the end of the presentation or follow up via email. Also, a copy of this presentation will be posted to our website at a later date. Today you will learn important supercritical fluid properties, how to select pump components and why, how potential problems are identified, what tips, techniques are used to solve them, and other solutions for specialized problems and applications. This presentation will focus on CO2 applications that may apply to other supercritical fluids. Teledyne ISCO pumps are used in chemical, pharmaceutical, or oil and gas industries for research and development, pilot plant, and industrial applications. These applications include injection molding and extrusion, where CO2 is ejected for foaming or reducing melt temperatures. Chemical feed or reactant feed for product and process development, including pharmaceuticals. Core footing or analysis for porosity and permeability studies of rock cores or foaming in the use of proppant materials. Other applications include carbon sequestration, biomass, biofuels, or cleaning. Shown here is the typical setup for connecting an ISCO pump to an extruder. An ISCO pumping system consists of either a single pump with a controller or a dual pump continuous flow system connected to the port of the extruder. The extruder connection line usually includes either a restrictor, a back pressure regulator, or some kind of restrictive orifice. The restriction prevents backflow, though a check valve can also be used. It's important to heat the expansion point, prevent the plastic from freezing and plugging the line. When the pump is usually run in constant flow mode, it can be started in constant pressure in order to reach steady state faster, then switch to constant flow. This is a particularly useful technique when operating at low flow rates. Optimizing requires an understanding of the cell nucleation and growth process, solubility of foaming agents, and the pressure volume temperature, PVT, conditions. As shown here, core flooding applications usually consist of a dual pump continuous flow system to deliver fluid through the core either direct or via an accumulator. A third pump operating at constant pressure, shown above, is to provide the overburden or confining pressure of the core. In this system, the dual pump system will force fluid then either into the accumulator with fluid out or directly to a core sample. Then as the fluid flows through the core sample, we monitor the pressure drop across the core. A back pressure regulator is used to maintain system pressure. The setup for delivering CO2 through the core is similar with a delivery pump connected to a CO2 reservoir. CO2 can be used for foaming in proppant material tests. Optimizing requires an understanding of how to achieve steady-state flows for recording the pressure drops across the core. And again, the pressure, volume, temperature effects and mass flow rates. A chemical reactant feed application, including pharmaceuticals, consists of a batch reactor or fall-through reactors, including microreactors. Usually you have two pumps delivering multiple fluids into a reactor or through a flow-through reactor or a microreactor. There are many types of pumps used for reactions, but Teledyne ISCO pumps, such as the D-series syringe pump, can deliver liquids or liquefied gases with flow rate accuracies of plus or minus 0.5% for long periods. Optimizing requires an understanding of how to achieve accurate and pulseless flows, and again, pressure, volume, temperature effects and mass flow. What defines a supercritical fluid? For CO2, it is anything above the critical point of 31.1 and with a critical pressure of 72.9, Then as the pressure temperature chart shows, any fluid above the critical temperature will be considered a supercritical fluid. And this fluid then will have gas-like fluid properties where the fluid cannot be compressed back into a liquid regardless of how much pressure is applied. And fluids in the supercritical state will have strong solvating and diffusing properties. When considering the system components of supercritical fluids, you need to understand the fluid state at pressures and temperatures, and for each system component, that is, at each point in the system, is it either a gas or a liquid. You need to understand the wetted materials and are they compatible with CO2. Compatible plastics or plastics are not compatible may have the supercritical fluids may permeate the material and then cause problems on decompression. Also, pumping system requires fluids to be in a liquid state in order to pump properly. A typical system consists of, starting from left to right, a CO2 source or tank, an inlet valve between the tank and the pump, then a pump with a circulating bath for cooling, an outlet valve between the pump and the user supply device, and then a user supply device, which consists of either an extruder, reaction vessel, or core holder. Then finally a restrictor to maintain pressure in the system. The CO2 tank is usually an industrial grade tank with a dip tube. The dip tube draws fluid from the bottom of the tank to ensure supply of liquefied CO2. The tank filter is required, especially for industrial grade tanks, to prevent plugging of the restrictor. Industrial grade tanks often have debris in the tank, which can flow out of the tank and then plug the system. We also have a laboratory grade tank with a dip tube. The laboratory grade are typically cleaner CO2. When placing the tank, be sure to consider the temperature effects on the vapor pressure. Outdoor tanks may have refilling with cold temperatures, such as cold temperatures in the wintertime. When connecting up the inlet line, a tubing length greater than 30 to 50 feet or 10 to 15 meters may cause too much pressure drop. While 1/8-inch stainless steel tubing is used for most applications, consider using 1/4-inch or 3/8 tubing for long distances or outside applications. Manual valve, a check valve, or automated valve required to close after refilling to prevent backflowing into the tank. The Teledyne Esco syringe pump is a positive displacement pump with a large volume for delivery of liquids or liquefied gases. It is driven by a DC servo motor with a single gear train. Piston speeds can be controlled separately for fluid delivery or refill. This is particularly important when the refill rates need to be slowed down to improve filling efficiency. That is, if you have a delivery flow rate of, say, 10 mils a minute, the maximum refill is 204 mils a minute, but you can reduce the refill to anything between the 10 and the 204. Starting from top to bottom, the wetted materials of the syringe pump are the pressure transducer, which is made of titanium. The cylinder cap is nitronic 50, and nitronic is usually more corrosion resistant than stainless steel 316. That transducer seal is gold-plated. The cylinder cap seal is a blue tinted Teflon seal. The piston seal retainer is nitronic. The piston seal is graphite-filled Teflon, and the wear ring below the seal is made of PEEK. The wiper seal is graphite-filled Teflon, the same as the pressure seal. And this, finally, the cylinder is made out of nitronic. All the wetted standard materials of an Esco syringe pump are compatible with CO2, and no additional modifications are necessary. When compressing a gas, such as CO2, heat is generated, and that heat must be removed to keep the fluid below the critical point of 31.1 degrees C in order to achieve efficient fills. An optional temperature control jacket can be added to the pump to remove the heat. Also, as a safety note, do not heat the CO2 while it's in the pump. The pump could become overpressurized as the fluid expands. Fill efficiency is defined as the volume at pressure divided by the total volume as shown in this illustration. With good fill, 60 to 80% fill, the total volume is expected. For example, a 100 ml pump should have 60 or 80 mils of usable fluid after the pressure is reached. Poor fill efficiency is usually commonly caused by high pump temperatures or empty supply tanks. The optional temperature control jacket is slid over the pump cylinder. It consists of two O-rings located at the top and the bottom for sealing, an inlet port located at the bottom, and an outlet port located at the top. The fluid entering jacket will come in direct contact with the cylinder to remove or transfer heat. Temperature control jacket for ISCO pumps are rated from 0 to 100 degrees C operation. The jackets are typically used with water baths, where the bath volume is 2 times the cylinder volume. For example, a 500D with a volume of 500 mils should be used with a water bath that has a volume of approximately 1,000 mils. The outlet lines are usually 1/8 inch stainless steel tubing capable of up to 10,000 psi or 689 bar. Pump outlet port fittings are usually 1/8 inch Valco rated at 10,000 psi or 1/8 inch NPT ports rated at 7,500. A manual valve, check valve, or automated valve required to close during refilling and open when delivering the fluid. The user-supplied device can either be an extruder, molding machine, reaction vessel, or core holder. The key component is the restrictor, which maintains the system pressure. Also, the restrictor must be heated due to the Joule-Thomson effect, as the gas expands, it will cool. Restrictors consist of either a linear tubing or a variable restrictor, such as a back pressure regulator. The typical sequence for system operation begins with refilling, where the outlet valve is closed, the refill valve is open, and the tank valve is also open. Note the tank valve should always be open. The pump is refilled until it's complete, and the entire system now should be at tank pressure. In placing the pump in delivery mode, the refill valve should be closed, the outlet valve should be open. Then the pump is run in constant flow or constant pressure until the pump is empty. Then you repeat the refill. If dual pumps are used, and the flow is continuous and refilling is automated. Next, we will cover pump selection. The basic specifications of Teledyne ISCO pumps range with pressures up to 268 bar or 30,000 psi, sub-microliter to 408 mils a minute flow rates, and flow rate accuracies are plus and minus 0.5% or better. Our standard products consist of either a single pump or dual pumps. The model name of the single pumps represent the nominal volume of the pump. For example, a 30D holds 30 mils, while a 1000D holds 1000 mils. A dual pump system consists of 2 single pump models, a controller, and a valve package. Valve packages are available either air, electric, or check valves. When combining an air valve package with 2 Model 500Ds, the system is called an A500. For electric valve, the system is called an E500. There are 8 standard pump models. The graph shows the 8 pump models on the bottom on the x-axis. The flow rate is shown in blue, and the pressure ratings of each pump are shown in red. Note that the 1000D, located on the far left, has the largest volume, it has the highest flow rate, but the lowest pressure rating. On the other end, the 30D has the smallest volume and the highest pressure. All the other pump models are in between. When selecting a pump for supercritical fluids, the 500D is the most common for pressures up to 3,750 psi. And the 260D are the most commonly used for pressures up to, say, 500. When selecting pumps based on flow rates, note that there is a difference between single and dual pumps. Continuous flow systems have a switchover algorithm for pulseless flow, and that lowers the overall flow rate. Therefore, dual pumps have a lower flow rate than single. For example, a single 500D is rated at 204 mils a minute, while dual pumps are rated at 132. The Teledyne ISCO controller can operate up to 4 pumps independently, or up to 2 continuous flow systems. The controller has a wide selection of built-in operating modes. For single pumps, you have constant flow or constant pressure, and the set points for these two modes can be set on the fly. That is, while the pump is running, you can change the flow or the pressure. Or with a computer, you can set a string of changes. We have built-in pressure gradients collections or flow rate gradients. We also have a dispense mode where you can deliver a pre-selected volume. For dual pump, multi-pump modes, you have continuous constant flow rates or continuous constant pressure, and in these modes, one pump will automatically refill, but the other one is delivering. We have a modifier mode, and we have a 2-pump concentration gradient mode. The controller also has a full range of external communications. Standard are 0 to 10 volt inputs. We have RS-232 and USB for serial communications, RS-485, RTU, and Ethernet TCP Modbus, and digital run and stop. For options, we have LabVIEW drivers. We also have a universal driver if you're developing your own software. We have 0 to 10 volt outputs and 4 to 20 milliamp inputs and outputs. Multi-valve options for continuous flow delivery are either check valves, electric valves, or air valves. There are also valve options for automation of a single pump with either air or electric, where you have an automated inlet and outlet that will open and close as the pump delivers and refills. For manual operation, we have manual valves for the inlet and outlet. There are several factors considered when selecting valves. Electric valves are designed specifically for CO2, and all the wetted materials are compatible. The valves are powered by the controller, so everything in the entire system is self-contained. For air valves, they need an upgrade of Teflon seals for compatibility, and also they require an air supply source to operate. However, air valves with the upgrades are sometimes best for use in 24/7 industrial applications such as extruders. Next, we will discuss troubleshooting. In this section, we will learn how to identify problems and solutions for system leaks, poor fills, temperature control jacket problems, the dual pump continuous flow system stops on its own, pressure transducer errors, restrictor instability, and low flow fluctuations. Leak checks should be performed routinely, but especially with the initial setup. The leak checks performed by setting the pump to constant pressure mode, then note the changes in the volume remaining over time to determine the leakage rate. Also, we have a field verification procedure that gives more details on this procedure. Leaks can be isolated by checking the lines and systematically opening and closing the valves. Note the CO2 tank valve must always be left open to prevent overpressurizing. You dead end the outlet line, either before or after restrictor reservoir, depending on whether you want the reservoir to be included in the leak check. Then you would bubble check the line between the tank and the pump inlet valve using tank pressure. Next, all the valves will be closed and you leak check the pump. And lastly, you'll open the outlet valve and leak check the entire system. Poor fills can be caused by no CO2 tank dip tube, an empty tank, or inlet lines are either too small or too long, which create unnecessary restriction. CO2 tank temperature too low, which causes the vapor pressure to drop. This can be resolved by adding a tank heater or put the tank in a heated environment. But be careful, do not overheat the tank. You can have pump temperatures that are too high, which causes CO2 to become supercritical when entering the pump. In this case, add a temperature control jacket to reduce the heat. For best results, operate the temperature control jacket at 5 to 10 degrees C. Note that condensation is possible on the cooling jacket, outside the cooling jacket, in high humidity environments. In that case, add insulation around the pump and the temperature control jacket, and also sometimes include insulation around the inlet and outlet lines. If temperatures are less than 0 degrees C, you may have ice built up in the cooling jacket, which is why 5 to 10 degrees C is usually recommended. The inlet into the cooling jacket should be on the lower side, and having fluid enter the lower, they will push fluid out the top and also push air out the top, and therefore prevent air voids, which could reduce the cooling effectiveness. Dynesco pumps have a poor fill alarm feature that notifies the user that the CO2 tank is too low for monitoring by monitoring the fill efficiency. The poor fill alarm is settable in the controller and measures fill efficiency for every automated refill. To operate, set the minimum allowable fill in percent. Usually setting a 30% or greater fill is recommended. That is, if the fill begins at 80% efficiency with a new tank, then the alarm will not activate until the fill is less than 30%. What are the causes if a dual pump continuous flow system stops? In a dual pump system, you will start with both pumps refilling. Both pumps then, and when running, will run together. They will calibrate to match the pressures. One pump will continue on, the other pump will go into refill. When the first pump nears empty, the second pump will come up. The flow rates will remain the same. That is, when both pumps are run together, but the total output flow rate will be the same. They will match the pressures, and then one pump will take over for the empty pump. One of the most common problems are incorrect systems and setup. We have a technical bulletin, TB01, will give you a step-by-step procedure on how to set up the continuous flow system. Also note the pumps must be completely filled before starting. Also, you could have insufficient fills and the CO2 tank has gone empty. That will cause the continuous flow system to stop. Or you may have a back pressure restrictor instability. If the pumps can't match pressures, the pumps will not complete the calibration step and they'll go empty and the system will stop. Restrictor instability can be caused by restrictor plugging, which can be solved by sometimes adding heat directly to the restrictor, cleaning the tank filter on the inlet line, or sometimes adding an outlet filter before the restrictor to prevent restrictor plugging. Also, sometimes you may have a spring-loaded back pressure which is oscillating too much and creating pressure instability. And finally, another solution that may work in some cases would be to change from constant flow mode to constant pressure mode. Errors in pressure transducer calibration can also cause the system to stop. Continuous flow systems use the pressure information for each pump to produce the pulseless flow. If the pressure transducers drift apart, they can be corrected by using the zero pressure feature on the controller. Note this feature can only be used when the pressure transducers are at ambient pressure. Otherwise, you may introduce an error into the pressure reading. To operate at low flow rates of less, say, than 1 mil a minute, the completed leak check is previously discussed. The temperature must be stable to prevent the expense and contraction of fluids, such as may occur when the heating and air conditioning system come on in a room. Restriction must be stable. If there's excessive time to reach steady state with low flows, then set the pump to constant pressure, then switch to constant flow. Next, we'll review custom pumps and accessories. Custom pumps are available to operate at higher pressures. A 65 HP is available to operate at 24,000 psi, where a standard 65D operates at 20,000. A 260 HP operates at 9,500 psi, where a standard 260 operates at 7,500. And last, we have a 500 HP, which operates at 5,000 psi. The 500 HP is the most common pump for supercritical fluids, as it allows a larger volume combined with higher pressures. A 500 HP has a 500 mil nominal volume, the same as a 500D. Again, 5,000 psi as compared to a 500D with 3,750. the flow rate of the two pumps are the same. An A500 HP continuous flow operation is also rated at 5,000 psi, and the flow rate of 138 mils a minute is the same for both pump types. Another custom pump is a 500 SP, which is half the height for limited space applications. It has a 179 mil capacity compared to 500 mils for a 500D. However, the pressure rating and flow rate ratings are the same as a 500D. Additional accessories include an insulating cover for reducing temperature fluctuation. This is insulation that goes around the outside of the pressure transducer and cylinder. And then as the room temperatures will fluctuate as the heating systems, cooling systems come on and off, that will dampen the temperature reaching the cylinder and dampen the expansion and increase in or decrease in fluid volume, which can affect flow rates. Our temperature control jackets, which are available not only on all of our standard pumps, are also included the custom pumps. We have a high actuated pressure transducer, which is great for improving pressure control when operating constant pressure. This transducer has a specification of plus or minus 1% compared to our standard pressure transducers of plus or minus 0.5%. And last, we have a high pressure transducer option that's capable of operating up to 200 degrees C. This concludes the presentation, and we'll be happy to answer any questions you have. If you haven't already, please submit your questions using the chat feature. If we are unable to answer your questions today, we'll gladly follow up after the webinar. And we'll give a few minutes for anybody that has any questions to send in. First question is, how does the modifier addition work? Modifier addition usually requires 3 pumps, 2 pumps delivering CO2, the third pump delivering a liquid. You can set the flow rate of the CO2 pumps and then specify the liquid to be mixed as a percent of the CO2, so that is you can have a 10% modifier addition or 20% modifier addition. Another question is, can the pumps be controlled by the extruder? If the extruder outputs, say, 420 milliamperes or 10 volts, that can be connected with the pump, and then the pump that will change the flow rate to match the extruder's speed. The last question is, can the ISCO pumps be controlled by mass flow? The ISCO pumps are basically volume pumps, so you only control by the volume. If you know the temperature, then of course that can be converted in density, and then you can calculate the mass flow. So you can operate in mass flow, but not directly. We could have a wide variety of application notes and technical bulletins to help with your setup. Just take a look at our website, www.teledyneisco.com, then select pumps, then either select application notes or technical bulletins from the drop-down menu. We have a number of application notes and technical bulletins related to supercritical fluids. We have a number on supercritical fluid applications. We have how to operate a dual pump system and properly set it up. Field verification procedure for pressure, flow rates, and leak checking. We have a temperature control jacket, how to set up and operate. We have one specifically in CO2 applications and technical bulletins and tips on operation. Low flow rate operation. We have one on metering pumps that explains the operation of how the syringe pumps function. If you want to operate at high temperature or high accuracy, how to set up and operate that, and how to connect it, what kind of things are available, how to operate modifier addition, and last, diagnostic and troubleshooting. This is not a complete list of notes, but these notes contain a lot of information we covered today. For more information on pump and component specifications, again, visit our website at teledyneisco.com. And while you're there, also visit our online store where you can easily reorder the parts. That's store.teledyneisco.com. Here you'll get quick access to pump numbers, part numbers, and an easy reorder of maintenance parts. We'll always do our best to serve you, so be sure to let us know how if there's anything else we can do to help. If you have any further questions, you can contact me, Dale Clay, at the phone number, email address listed below, or you can contact our product line manager, Dick Dodavo. Thank you for attending our webinar today, and goodbye until next time.